Hmm. Hello, everyone. I'm going to talk about it's a homework problem in chapter 7 in energy conservation 7.57. Okay, okay, the problem is 7.57. Okay, here's the problem. It says, okay, yeah, it's an energy conservation problem, but you need a little more. Have to use more thought in there. Okay, so it says, there's a block called mass M. Okay, so the mass is 190 gram block, and it's mounted on initially it's mounted with a spring. And initially, it's compressed. It's compressed. It's the mass amount on the spring and compressed 15 centimeter. And the spring constant of the spring, the force constant of the spring is 200 Newton per meter. And initially it's compressed and then it's released the system. It's released. Okay, so the object will then do the motion. Okay, and you do the motion and the motion when you do the motion. So here is frictionless surface, and it will pass through a rough surface and give you the friction coefficient nu equal to 0.27. And after releasing this object passing through this rough surface and go to a curve, and this curve is frictionless. So it will climb up to the curve and then okay here and climb up to the curve and then velocity because the climbing up. Okay, the gravitational force will slow down the object when he goes up. And it goes while the velocity decreases to zero, and then the gravity will pull this mass down, okay, and all the way back down, and then pass through this surface again, and then after releasing the object, this friction, this sweep spring back to its original position, and then it will it will become like a very hard object. Okay, so when the object going back to from the curve passing through the surface the spring never compress anymore. Okay, it just it just directly bounce back to this rough surface again and go to the curve and all the way up again and go way up and then come back to the horizontal surface and hit the spring and then bounce back to the curved surface and doing a back and forth motion. Okay, so after releasing the object will doing the motion between this section. Okay, it's released and goes up and goes down and then hit the spring and then bounce back and go to the surface again, curved surface again, and then goes back, hit the spring, and then bounce back, go back to the surface, go back to the curved surface again, back and forth, and finally it will stop right here. Okay, stop at the friction rough surface, and it said measure after its launch, where does the block finally come to rest? And it must come to rest at here. Okay, in this region, it must come back to rest as region, and I will explain why. And measure from the left end of the friction zone. Okay, it said okay, it will stop at here, and what's the distance? And what's the distance? And the reference of distance is from the left end of the friction zone. So the left hand of the friction zone is here. What's the distance? Okay. So this is also energy. This is an energy conservation problem, and yeah, but I think this problem doesn't give you detailed information, or the detailed information is what I just said. After releasing this object, okay, and the spring become rigid, okay, after releasing the surface, after release object, the spring go back to its equilibrium. Initially, it's compressed and then it's released. And after release object, this spring is become a very hard object. Okay, it's never compressed and it doesn't compress anymore. Okay, after releasing, the spring never compress anymore. So this object just go to the here and back to here. Okay, keep doing the back and forth motion during this region. Okay, but I think the problem didn't state that point. Okay, that's why I make this video for you. Okay, after releasing an object, the spring become very rigid. Okay, and never compressed again. Okay, so how to solve this problem? Okay, let's back to okay. I have a graph here. Okay, okay, yeah, that's a schematic representation of this problem. Okay, so initially, okay, let's first of all, okay, initially it's compressed 50 centimeter, right? Okay, so initially it's compressed 15 30 meters. So I think initially, okay, let's draw. Nah, maybe I use ruler is better. Okay, let's use a ruler. Wow. Da, da, da. Okay, initially, okay, let's say initially here, okay, initially the spring is compressed and it's 15 centimeter. Okay, in this problem we will use the energy conservation. Okay, let's calculate the total energy of the system as it's among as the initial compression. Okay, so the so the energy of the system is okay, kinetic energy plus the potential energy. Okay, the kinetic energy, because initially when we compress the mass compress the spring and initially it at rest, so the kinetic energy is zero. Okay, but initially this is velocity is zero. Okay, velocity is zero. And the potential energy, here we in this class we have two kind of potential energy: gravitational potential energy and elastic potential energy. And for this problem, do we have to consider gravitational potential energy? Kind of, but we can set so. But in this problem, we set the origin, the height origin here. Here's the origin of the height. Okay, here's origin of height. I set the y-axis. The origin of y-axis is here. It's zero. Okay, so initially this mass is on a horizontal surface, so it doesn't have the gravitational potential energy because I said the height here is zero. Okay, horizontal surface height is zero. Okay, so there's no potential gravitational potential energy, but it has elastic potential energy because it's compressed the spring for 15 centimeter. So we have the spring potential energy or elastic potential energy. So it's kx squared. What's the force constant or elastic force constant for the K? Okay, the K force constant K is equal to 200 Newton per meter. So okay, K x squared and the compression value is 15 centimeter. 15 centimeter means 0.15 meter. So 0.15 meter and then square. Okay, it's using use the calculator to calculate the total energy at the initial state. Okay, what's the energy? Let me see. It's 2.25, 2.25, and the unit is joule. Okay, and then after compression, after system releasing, so it goes the object doing the to start to do some motion and pass through the rough surface and then climb up the curved surface. And then he will going back on the surface and then back to the horizontal surface and and all the way back to hit the spring. And I just say after releasing the object, the spring become a very hard object. So it never compress anymore. So when the mass go away back to hit the spring, it just bounce back and then do another motion. pass through the rough surface and climb the surface again. So the object will keep doing the motion in this region, okay, and finally it will stop at here, okay, because it is a rough surface, and rough surface you have friction, and friction, and the work done by the friction is always dissipate your energy, and let's calculate the work done by the friction, okay. Let's calculate the work done by the friction. Okay, what's the work done by friction? Because it always dissipate your energy, so it's negative, and it's the friction force and times the distance. Okay, so there's a problem. What is the friction force? What's the friction force in this problem? And it gives you the friction coefficient is nu equal to 0.27. Okay, so in previous lecture we see the friction force equal to a friction coefficient and times your normal force. Okay, and here is the free body diagram of this mass when it moving on the rough surface. And yeah, there is no acceleration when it's moving on. When moving on the surface, it only have the horizontal. It's doing the horizontal motion. There is no acceleration on the y direction. So so at this situation, your normal force is just equal to your weight. So it's equal to nu and mg. Okay, so we can, if with this information, we can calculate the work done by the friction. Okay, so it's minus nu mg and times d. Okay, it's minus, okay, nu is 0.27 and times the mass of object. I remember is, what's the mass? What's the mass? Oh, 190, okay, 190 gram, right? 190 gram. Where's my pen? Okay, mass is 190 grams, so it's 0.19 kilogram because we want to use the MKS system. Okay, and the acceleration of gravitational force, acceleration, gravitation, 9.8. And what's the distance between this rough surface? Okay, the length of this rough surface, I think the problem say it's 85 centimeter, right? Do you remember the problem? This is 85 centimeter. So 85 centimeter is equal to 0.85 meter. So it's 0.85 meters. Yeah, I want to put everything MKS system, meter, kilogram, and seconds. Okay, so we can find the work done by the friction. What's the value? Yeah, you just use your calculator. Let me see what's the value. It's a minus 0.427. And units is joule. Okay, so it just tell you every time when this mass passes through this rough surface, your total energy, you will lose 0.427 joule energy. Okay, every time when the mass passes through this rough surface, every time when the mass passes through this rough surface, it lost 0.427 energy. Okay, 0.427 joule energy. Okay, this is a very useful information because it will help us to determine the final answer. Okay, so like I said, after releasing the mass, the mass is doing the motion in this region back and forth. Okay, so just right after releasing, the total energy is 2.25 joule, right? 2.25 joule. Okay, and then every time it passes through the rough surface, it's lost 0.427 energy. So when you pass the first time, what energy will be? Pass the first time. You can use the calculator, calculate yourself. Pass one time, 1.823. And pass the second time, 1.396. Pass another time, 0.969. Passing one more time, just keep reducing the amount, the same amount. Why two? Because there's only friction in the rough surface. The other region, there's no friction force. So only this central part, the rough surface part causes the energy. The other part, no friction. So the total energy, energy always preserved. Okay. Okay. So and then 0.55542, and if you're doing one more time, 0.115. Okay, and then one more time, it will stop. It will start. The total energy will become zero. Okay, because it will pass it one time, it will cost you 0.427 joule energy. So once you at this situation, your total kinetic energy is 0.115. You're doing one more time, it will become zero. Okay, so let's see, and let's make a mark notation here. Okay, here is okay. Just this is just starting point right after releasing, right after releasing, right after releasing, right after releasing, and then it passed the first time. The first time, it's climbing up. Okay, climbing out the surface, and then goes up, and then it goes back and goes back to the horizontal surface and pass through the rough surface again. So it's a second time. Okay, and then hit the spring. Okay, and I said before, after releasing the spring, it's become a rigid body. So when the mass hit the spring, it doesn't compress anymore, and then it bounce back to the horizontal surface, bounce back to a rough surface again, and do the climbing up again. So it goes up, okay, and then goes down again, goes down again, and then goes up. Okay, and then goes up again, and then goes down. Okay, and then goes down. So we have to take care about this. Take care about this. It goes down. So what's the situation? What's the final situation here? Okay, let me do a little graph. Okay, the final situation it will like this. Okay, the mass is here. Here is, and then this is a rough surface. It's a rough surface. Okay, and the mass it's just back from the curved surface. So it will be here. It will be here, and then your total kinetic energy is 0.115 joule. Okay, and then when you go past the rough surface, it will stop. Okay, it will start at a very a certain region here. The problem I want to ask you, what's the where it stopped? Okay, where it stopped. So this energy conservation problem. Okay, what's the energy conservation problem here? At this point, yeah, it doesn't have there's no spring, and it's back to on horizontal surface. So it doesn't have the gravitational potential energy more. So actually, this is your at this moment you only have the kinetic energy. Okay, so let's do the energy conservation. Okay, delta K plus delta U equals to Q plus W external force. And the heat, like in previous lecture, I said heat is caused by the friction. And the whole system, yeah, no spring. Yeah, well, now we don't have to consider spring. After releasing, we don't have to consider spring. So no elastic potential energy. And furthermore, okay, it's right now it's moving on the horizontal surface. Right now it's back to the on the horizontal surface. So there is no gravitational potential energy. So no elastic potential energy and no gravitational potential energy. So this term just ignore. Okay, and there's no external force done on the system. Okay, so we will finally reach the final equation. So it's Kf minus Ki equal to Okay, the friction force. Okay, it's minus its friction force. Like friction, we say it's nu mg, and this term we don't know. This we want to solve. We want to solve this d because we want to we want to solve how far it will after moving what distance, at what position it will stop. So this d is we are going after. And from this system, the final kinetic energy is zero because it finally stopped. So that's why its final kinetic energy is zero because it stopped. There's no velocity, so there's no kinetic energy. So this will be zero. And your initial kinetic energy is 0.115. And the minus is friction coefficient and your mass and your gravitational acceleration and the distance you don't know. Okay, here we will have the equation like this. Okay, so this very easy equation. Okay, and you just use the calculator. What is D? Let me see. Just give you the answer. The D is 0.229, and the unit is meter. Okay, so it's equal to 22.9 centimeter. So So the D is here. Here is D. So here is D. So after when you go back, when you go into the rough surface, it will move about, yeah, maybe it's not right in the scale. It will move 22.9 centimeter and it will stop. Okay, but the problem I want to ask is because of the reference point in the problem is, let's go back to this problem. The reference point is the measure from the left end of the frictional zone. Okay, measure from the left end of the frictional zone. So the reference point is from the left of the frictional zone. So it tells it wants you x this position. Okay, well, sorry, this distance because reference point is here. Okay, this is the problem asking for. Okay, it's not me. Okay, it's the problem asking for. So this is 85 because this is total distance is 85. So minus 22.9. So that's the answer. The answer is 62.1. Okay, 62.1, and unit is centimeter. So this is the answer, 62.1 centimeter. Okay, so this is an energy conservation problem. Okay, but you need to have do a little brainstorm to get the answer. So that's why I make the video for this problem. And yeah, and also yeah, like I say, okay, after releasing, the spring is become a very rigid body, so it never compress anymore. So after releasing, just the mass just bounce back between the curved surface and the horizontal plane, doing the back and forth motion. So let's I have to explain this. I have to explain this because the problem didn't state it very clearly. Okay. Okay, so this problem 7.57. Okay, hope you understand energy conservation more. Okay, I'll stop video here. See you in the next video. Bye bye. Ah, yeah, yeah, yeah.